Look at this flat, two-dimensional graph as it lifts off the page and warps into a three-dimensional space curve. Standard calculus operates almost entirely on uniform, flat axes, like the one we started with, but physical reality does not. When we calculate physical properties, like the mass of a curved wire bending through space, or the energy required to push a fluid through a twisting pipe, we are operating along complicated three-dimensional paths. This creates a central mathematical problem. Our basic integration tools are built for flat, straight lines. How do we apply them to curved, multidimensional geometry? This diagram illustrates the solution: parameterization. Parameterization is a mathematical method that maps coordinates from a complex space into a simpler one. Here, we take a 1D parameter, usually represented by the variable t for time, and use it to systematically unspool the wire, pulling the curved 3D geometry back into a flat, straight number line we can easily integrate over. But mapping a curve onto a straight line has a direct consequence. Translating the geometry distorts the space. Segments of the curve that are physically long might be compressed into a short time interval, while short, tight curves might stretch out. To correct for this geometric distortion, we have to introduce a mathematical correction. We call this the stretching factor. Evaluating any spatial integral requires applying a specific stretching factor. Without it, your flat calculation will completely misrepresent the physical object. Mastering multivariable integration means mastering how to calculate this precise stretching factor across different geometries and different mathematical fields. We begin with the first core application, the scalar line integral. This operation sums a simple magnitude, like temperature or density, along a one-dimensional space curve. The formal definition of the scalar line integral integrates a function over a curve C with respect to physical arc length, dA. To execute this, we transition into flat parameter time dt using a parameterized curve, r of t. Notice the term multiplying dt. That is r prime of t, the magnitude of the tangent vector. This term acts as our exact stretching factor, correcting the distortion between parameter time and physical space. We evaluate a scalar function over a semicircle, parameterizing the curve using x equals cosine t and y equals sine t from 0 to pi. Taking the derivatives computes the stretching factor. The radical simplifies beautifully to exactly 1. When we apply that stretching factor of 1 to our specific function, the integral simplifies perfectly to the bounds of 0 to pi, yielding a clean final calculation of 2 times pi plus 1. This specific example featured a uniform stretch of 1, meaning parameter time matched physical distance perfectly. More complex curves, however, produce dynamic stretching factors that change constantly along the path. For scalar fields, the rule is strict. The physical length and curvature of the geometry directly dictate the mathematical stretching factor. We now shift focus from static magnitudes to directional forces. This requires the vector line integral. This animated diagram models the concept of work. Work is a physical calculation that measures the energy exerted when a particle moves through a directional force field, like gravity or a magnetic current. A major shift occurs here. The absolute path length no longer matters. We only care about how much the external force field aligns with our specific direction of travel. Mathematically, the scalar stretching factor is replaced. We take the dot product between the field and the velocity vector. Let's test this by applying a specific vector field to a segment of a circular path, evaluating from t equals 0 to t equals pi over 4. We will analyze the field where the vector components are f of xy equals xyi plus yxj. We execute the integral by composing our vector field with our path, and then finding the dot product between that composed field and the path's derivative. By integrating the resulting trigonometric functions over our bounds, the calculation reveals a total work value of 0.285. For vector fields, the mathematical stretching factor transforms into an alignment factor. It actively filters out any perpendicular forces to measure the true work accomplished. Parameterizing complex paths and calculating dot products requires heavy, tedious computation. This raises a conceptual question. Under what conditions does the specific route taken between 2 points become entirely irrelevant to the final calculation? The answer lies with conservative fields. A conservative field is a vector field that acts as the perfect gradient of a scalar potential function. The gradient simply points in the direction of steepest increase for that function. If a field meets this condition, we can use the fundamental theorem of line integrals as a massive mathematical shortcut. Because of the chain rule, the integration process entirely collapses. You do not need to evaluate the internal path. You simply evaluate the potential function at the start and end points of the curve. This diagram evaluates the expression 2x squared y dx plus x cubed dy from t equals 0 to t equals 1. You could choose any tangled path to compute the work, but instead we identify the scalar potential function that generates this vector field, which is x cubed y. By applying the boundary conditions of t equals 1 and t equals 0 directly to the potential function, the calculation instantly resolves to exactly 2. When a field is perfectly structured as a gradient, the physical journey is rendered meaningless. Only the absolute boundary conditions dictate the work done. We can now escalate the dimensional complexity, transitioning from evaluating 1D wires and paths to full 2D shells and surfaces. This split-screen diagram illustrates the upgrade. Mapping a 2D surface requires expanding our flat parameter space. Instead of a single variable t, we now use a two-variable grid, defined by u and v. Recall that 1D distortion was corrected by measuring the length of a single tangent vector. The 2D equivalent is measuring the surface area of a warped parallelogram directly on the 3D grid. We calculate this area mathematically by taking the cross product of the two tangent vectors, tu and tv, finding the magnitude. We can prove this concept by parametrizing a unit sphere. We map the surface parameters utilizing the spherical coordinates theta and phi. To find the area of these spherical patches, we calculate the Jacobian determinant, a matrix of all first-order partial derivatives that quantifies how the local space is transformed. This determinant is the algebraic equivalent to our geometric cross-product magnitude. For this spherical mapping, the determinant simplifies to the absolute value of sine phi, providing the precise scaling factor required to integrate over the sphere's surface. Moving to higher dimensions doesn't alter the mathematical philosophy. It merely upgrades the stretching factor from a 1D vector length to a 2D vector area. Stepping back, we can view the entire architectural landscape of the spatial integrals we just covered. All spatial integrals are simply flat integrals modified by a specific geometric transformation. This matrix grid isolates the scalar fields. You can see how both dimensions rely heavily on absolute magnitudes to map physical space. Looking at the vector row, the requirements shift entirely to directional alignment, utilizing dot products to filter out unnecessary forces. Whether the equation asks for length, area, dot products, or cross products, the stretching factor serves as the universal translator between abstract 3D geometry and calculable numbers. Mastering these parametrizations and the geometric role of derivatives provides the foundational framework needed to analyze the complex physical systems that define our spatial reality.